Okay, so last thing we want to talk about here in chapter 1 is making approximations and assumptions. Often, we're going to deal with situations where we cannot measure something directly. So, for example, if I wanted to determine how far away Tampa is from Xenia, where I live, that is kind of a weird thing to calculate because I can't like pull out a measuring tape and like run to Tampa with it, right? Now I could Google it, but if I'm in a situation where I can't do that, I could make a couple of assumptions. I've been to Tampa to visit my dad in Florida before, and that trip took me about 14 hours. So I can say, yeah, sure, speed limit was about 75 when I drove there, and I can estimate it's probably about 1,050 miles away, which is 75 times 14. That is a rough ballpark estimate. It's not exactly correct. But, for making an approximation in a situation where I can't measure or look up the actual value, it's not bad. The actual distance is about 970 miles. So 1,050, close enough. Not off by that much. I could also say something to the effect of, okay, so that Ford pickup's about twice as big as my Honda Civic. I know my Honda Civic's like about 2,500 pounds, so it's probably about 5,000. Again, this is not an exact value. I'm sure I could look up that make and model of truck if I wanted to know exactly how much it weighed. But in a situation where I can't do that and I have to make an assumption, that's a safe assumption to make. So often, we're also going to be using averages. Averages are going to be our friend for making assumptions. A lot of the time, when we can't make measurements, we can make averages and use the assumption like, okay, this is an average situation. For instance, a person, the average human weight is about 75 kilograms. So whenever you're doing, an back of the envelope calculation involving a person, you can say they're probably about 75 kilograms. If they're from the United States. Rest of the world's a little bit lower, I think. I think average globally is about 70. So assumptions are very, very useful. They can help us assign a number to things that are hard to get numbers for. A couple of examples are actually problems I've solved in my high school class that I teach. In this one, if we want to find out how tall Godzilla is, right? I'm sure there's a canon height that he has on some nerd website somewhere, but let's say I want to know how tall Godzilla is and I'm just eyeballing it. I could say, hey, he's standing next to this building. I could count how many stories are here and make the assumption, using average story height, how tall Godzilla is. So I can determine his height based on how tall this building is and how many stories I'm counting relative to his head to torso height. That would give me a decent estimate. Also, let's say I wanted to figure out how heavy Cloud Strife's sword is from Final Fantasy VII. So if I want to know how heavy this sword is, figuring out the sharp, like the angling of the blade and like the fact that it's got a handle here and like the fact that it's curved on not curved, sorry, triangular, angled on the edge. It's got materia here. There's markings in it. This thing would be pretty hard for me to figure out how heavy it is without actually weighing it. But sadly, this is a video game, so I can't do that. What I can do, though, is just look at this thing and say, okay, this is a prism, basically a cube made of iron. And I can estimate Cloud's height. Say he's an average height guy. In fact, I could go to Google and look up what his canon height is. I think he's 5'7", if I remember correctly. I'm pretty sure Cloud is 5'7". But using that, I can estimate how long his sword is, and therefore how wide his sword is, and about how thick his sword is, and then I can try to figure out how big it is, say it's made of pure iron, and call it a rectangle of iron to get a rough estimate for his sword. So this way we can kind of, eyeball and get a rough idea for something if we're in a situation where we can't easily measure stuff. This is kind of fun, at least to me. I really like to watch movies and play games like this where I'll see a thing and be like, that doesn't make sense. How heavy is that thing? Cloud swinging a sword this big and this heavy is pretty rough, by the way. Okay, so let's do our last problem of Chapter 1 together before we get into the math review. And I'll switch it over to live action ASA as we solve this here in a moment to give you some information, but I want you to come up with a plan to solve this problem, describe the assumptions you need to make, as well as any information needed in the process to go about coming to a reasonable estimate. So try to figure this question out. Your answer could be totally different than mine. That's totally fine. We just want to see how the process works. So how long would it take a person to drink the Atlantic Ocean? Think about what you need to find out. Think about what assumptions you can make, and see if we can come to an answer. Pause the video right now and then come back in a minute and compare your answer to mine. Live Action ASA back one last time for Chapter 1. Here's what we're going to do. We want to figure out how long it will take for one person to drink the ocean. For this, we need to get some data on how quickly a person drinks. For this problem, we're going to have to make a couple of assumptions. The first one is that I am an average person, and that the average person is going to drink salt water at the same speed that I drink Diet Coke. The other assumption we're gonna have to make here, obviously, is that like I don't need to eat or sleep, and I'm just gonna be doing nothing but drinking ocean water as fast as I possibly can. Again, this is a Fermi approximation, so we are not going necessarily for accuracy. We're going for ballpark estimate on the amount. So those assumptions are probably fine for me to make. And also, we can assume that, you know, like, I'm not gonna get sick from drinking all that salt water, or my stomach's not gonna burst, or whatever, any of that stuff. We're gonna assume that it'll be fine, okay? So, let's see how long it'll take one person to drink the ocean. I have with me, in this beaker, the remnants of my 2 liter of Diet Coke, which actually just so happened to come out to almost exactly 400 milliliters. And I have with me here a stopwatch. So I'm gonna time how long it takes me to drink 400 milliliters of Diet Coke. We can then use this estimate, in the calculation of the problem to determine how long it should take. For science. Cheers. .50 seconds. Let's try to solve this now. Okay, so let's try out this last problem. There's a couple of things that we know now. I Googled the size of the Atlantic Ocean, volume of the Atlantic Ocean, rather, excuse me, and I got 354,700,000 cubic kilometers is the volume of the ocean. So that's the amount of water I need to drink. We also determined that the speed I drink water at is 400 milliliters in 9.5 seconds. So we want to move this around to get seconds on top. So I'm going to rewrite this as 9.5 seconds is how long it will take me for 400 milliliters of water. Now, all I have to do is convert cubic kilometers into milliliters. So let's go ahead and give that a shot. So 354,700,000 kilometers cubed. I want to convert this into milliliters. The first thing I should do is probably convert it from kilometers cubed into meters cubed. We know that 1 kilometer is 1,000 meters. But how many cubic meters is a cubic kilometer? Well, we're going to have to cube our conversion factor. So when I do this, I have kilometers cubed on the top. Now I've got kilometers cubed on the bottom. Those will kill each other. And then we've got 1,000 meters cubed on the top. I put the whole thing in parentheses to know that we have to cube this 1,000 as well. So whenever you're dealing with cubic or square units, we've got to keep in mind that conversion factor as well. Okay, so now I've got this in cubic meters. I want to go from cubic meters to liters. And meters, or sorry, a liter is equal to a cubic decimeter. So we can say that in 1 cubic meter, we have 1 decimeter cubed. That'll kill this. I'm sorry, excuse me, 10 decimeters cubed, forgive me. And then that gets cubed up top as well. Okay, so now we end up in this position. We have this in decimeters. I know 1 cubic decimeter is equal to 1 liter. That kills this piece. And then in 1 liter, there are 1,000 milliliters. Now we've got the ocean, the volume of the Atlantic Ocean in milliliters. Now all I have to do is multiply it by my drinking speed, which we said was 9.5 seconds for 400 milliliters. Okay, there are other ways you could do this too. If you wanted to, you could just Google the conversion factor from cubic kilometers to liters. You'll end up getting the same thing. In fact, that's probably easier to do than this. But just so you know, when we're dealing with a cubic volume, we have to cube the conversion factors too. Same thing with squaring if we're talking about area. Okay, so let's go ahead and do this calculation with my trusty handy calculator and see how we did. This is going to be a ridiculously big number. Let's hope my calculator can handle it. Times 1,000 times 9.5, and then that's going to be divided by 1, divided by 1, divided by 1, divided by 1, divided by 400. Okay, so I got 8.424 seconds times 10 to the 21st. That is a very big number. Okay, so I could put this in years. if I wanted to. And in fact, let's do that. That sounds fun. I just want to know for funsies, but that is the correct answer in seconds. Let's see what I get. So this in seconds. Let's see. In 1 hour, there are 3,600 seconds. Oopsie. Boop boop. In 1 day, there are 24 hours. Boop boop. And in 1 year, there are 365.25 days. So if I wanted to get this number in standard format, or sorry, not standard format, excuse me, in years, it's 10, so 8.424 times 10 to the 21st, 8.4. And that's going to be divided by 3,600, divided by 24, divided by 365.25. And we get 2,66940 451,745,380, which is 1,000 million billion quadrillion 266 quadrillion 940,745,380 years, which is thousands and thousands of times the age of the universe. So if I spawned in at the beginning of time and did nothing but drink the Atlantic Ocean, I would still not even be 10% of the way done. So, this is a Fermi approximation. This number is obviously ridiculous, but we have a ballpark estimate now. So, that brings us to the end of Chapter 1. Hope you guys enjoyed watching the video. There is one last thing I want to do, and that is math review. If you are comfortable with math, and you've taken a math class recently, you'll probably be okay. However, it's probably a good idea to at least look at the next video and make sure you understand how to do the problems I'm going to show you. Because this is going to be math that will be pretty imperative to success in Physics 1110. But until then, I'll see you guys next time.